So we would like to use the Greens theorem to find the work done by the force given by this vector on a particle that moves counterclockwise around the closed path given by these. That is, the path of the particle along which we are moving it is. So we are going to compute the line integral of the vector f that we have to work on along this path given by these three curves. So this is a closed region and this is a simple curve. So first we will recall what Green's theorem is. So this is our simple closed curve R, and it is enclosing the region. Oops, sorry about that, and let me just get a lighter color right here. Okay, and this is enclosing the region, say R in here. All right, so according to the Green's theorem, we can change the line integral of f along simple closed curve C, which is oriented counterclockwise in this case. All right, and here this amounts to the same as fx dx plus fy dy, and the Green's theorem is going to change this to this double integral, all right, taken over the enclosed region R. And what we can do now is that we will look at the, remember we are just simply doing this, that taking the analog of the Stokes theorem in the plane. Okay, so we will differentiate the second component partially with respect to x, minus we will have the derivative of first component with respect to y, and then we have our area element. So let's see how we applies this scenario in this example. So here you can see that our f1 is 3x squared plus y, and or rather fx is 3x squared plus y, and fy is 4xy squared. So we are going to take this right here, and first we have what? First here we have 4xy squared. Okay, so let's write that down. Okay, and then we have minus 3x squared plus y. Okay, all right, so this becomes equal to what? Let's just simplify this quickly, and then we will go ahead and look at our boundaries. So this will be what? 4y squared, right? Okay, because we are differentiating partially with respect to x, so 4 and y squared are going to be treated as constant. 4 and y squared will be treated as constant. Here we are differentiating partially with respect to y, so this is treated as a constant, so our value will simply be 1. Okay, so this is what we have to work on. So to compute the double integral, for this region R, what we will do is we will take an elementary region here. So what happens here is y ranges from 0 to square root of x, and our x is going to range from 0 to 9, and of course 0 to 9 will be the limits of the outer integral, and this will be the inner. So for this curve, what we have then is that first we look at the outer one, okay, and that goes from 0 to 9 for x, right? And then we look at the inner integral, right? Okay, and that goes from 0 to how? 0 to who? Simply is square root of x right here. And then what we are doing is that we are integrating this quantity, okay, and we are doing the integration first with respect to y and then with respect to x, right? And now rest is routine, but since we started it, let's finish it off. Okay, so here we go. So we got this integral and we'll work on it step by step. So first we have this ranging from 0 to 9, right? And let's do the integral. Here we go. Okay, so what we got is 4y square integrated with respect to y would be what? 4y cubed over 3, right? And here we got negative y, and then we have dx. So I'm sorry, the upper limit is, pardon me, okay, sorry about the phone going off. So this is square root of x, and the lower limit is 0. So this changes to, then if you look at it, it will be, okay, it is going to be, here we have for the first one 4y cube. So for y, when we put, when we put a square root of x, that's going to be x to the 3 over 2 divided by 3, and then minus, of course, x to the 1/2, and the lower limit will be 0, so we don't have to worry about it, right? So now this is a one variable integral, okay, and just leaving the details on you. Let's just finish it like the final value will be what? 558 divided by 5 units. So let me know if you have any questions, okay?